The range of a function is the set of outputs that are actually achieved by the function. For example, for this function, only the letters A, B, and C have arrows pointing to them, so they represent the range of f. When tasked with finding the range, one method involves first graphing the function. For example, if f is a linear function with non-zero slope, then its graph is a line in the plane. From a geometric perspective, the possible outputs lie along the y-axis, that is, they are represented by horizontal lines in the plane. To say that an output is achieved means that it's mapped to by the function f, which means that the horizontal line intersects the graph of f at some point. In the case of the function in this problem, we see that every horizontal line intersects our graph, and so this means that every possible output is actually achieved. Since the set of possible outputs is a set of real numbers, we can say that the range of f in this case consists of the set of real numbers. As another example, consider the power function x squared. For this function, the outputs that are actually achieved are those that lie above the x-axis. Indeed, whenever a horizontal line lies below the x-axis, it does not intersect the graph. This is because the function doesn't achieve any negative values. It only achieves non-negative ones, and in fact, it achieves every non-negative value. What this means is that the power function of x squared has range given by the set of non-negative real numbers. In terms of interval notation, this is just the set from 0 to infinity, including 0. Sometimes the set of non-negative real numbers is denoted by appending a subscript containing the relevant inequality sign. As another example, the exponential function 2 to the x achieves the outputs that are strictly above the x-axis, that is, the set of positive real numbers. So we can say in this case that its range is the set of positive real numbers from 0 to infinity. Notice in particular that the number 0 is excluded from the range because the function does not achieve the value 0. Here's a slightly more complicated example. In this case, the function is a quotient of two polynomials, both of which we could graph individually, but it's not quite so clear how to graph their quotient. One good thing to try when presented with a quadratic polynomial such as the numerator is to try to factor the polynomial. In this case, we're lucky, and the polynomial does split into linear factors, one of which is actually the same factor as the denominator. Now, we know that we can reduce a fraction by a factor common to the numerator and the denominator, provided that factor is non-zero. What this means for us is that when x minus 2 is not equal to 0, then our function admits the description of being equal to just 2x minus 1. In other words, when x is not equal to 2, the function is equal to 2x minus 1. Notice that when x is equal to 2, the denominator is 0, and so the function is not defined there. From a geometric standpoint, what this means for the graph of the function is that it has a hole at the point x equals 2, but otherwise the graph is equal to the line y equals 2x minus 1. The range is then found by considering which horizontal lines intersect the graph. In this case, the hole is at the output of y equals 3, and so this number is excluded from the range. In fact, this is the only number excluded from the range, and so the range is equal to the union of the interval from minus infinity to 3 with the interval from 3 to infinity.